Hi, my name is Matt Ozales and I'm an RF engineer at Keysight Technologies. In today's talk I'll go over the basics of how to design RF power amplifiers, and I think that this material should give you a good foundation for understanding how these types of circuits work. If you understand the material that I'm going to cover today, you'll also be able to build off of it to understand more advanced topics in the field of power amplifiers. The objectives of my presentation are first to define power from an AC perspective, and then demonstrate how power is generated and dissipated in a real power amplifier circuit. Next, we'll look at power amplifier operation from an intuitive point of view, and I'll build off this to define and discuss efficiency, and from there we'll look at how to set up a load line and how this is used in PA design. And I'll even share my workspace with you at the end so that you can explore the concepts that I'm going to talk about today at your own pace. Now, part of the workspace that I'm making available will be an interactive waveform generator, which will allow you to design, generate, and analyze your own RF waveforms in real time. And this will help you to understand these key concepts that we're going to talk about today. So all of the waveforms and examples that I'm going to show in this presentation were generated using this waveform tool. To understand RF power amplifiers, we need to begin with an understanding of power. Most RF engineers are familiar with power from a frequency domain perspective, but to be successful as a PA designer, you'll also need to understand power from a time domain perspective. Here I'm showing a set of sinusoidal voltage and current waveforms in the time domain, and each of these can be described simply by sine wave equations with an amplitude offset and a phase offset. We can obtain the average power from this by multiplying these waveforms together and calculating the area under the resulting curve, and then dividing by the time. Now, for the waveforms described by these equations, the integral works out to be simply a multiplication of 1/2 of the peak values times the cosine of the phase offset between the voltage and current. The peak values are, of course, half of the peak-to-peak values, so we can also express this equation in terms of peak-to-peak waveforms too, and knowing both expressions for power can be quite useful. So here I have a very simple circuit set up in the simulator, and this is just a frequency domain power source, and I'm going to combine this signal with a DC bias through a bias T, and then I'll run a harmonic balance simulation on this. In the data display, I'll look at both a frequency domain calculation and a time domain calculation for power. So in the frequency domain, since I have both a DC and an RF component, I'll get a spectrum at the output for voltage and current. And if I multiply the voltage and current spectra together, conjugating the current, I'll get a power spectrum. And you can see that both the DC and RF elements are 1/2 watt. Now, it's also easy to isolate the fundamental frequency component, as I'm showing here, so if I want to look at only the RF power, I can easily do that in harmonic balance by just indexing it, and it turns out that this is 1/2 watt. In the time domain, I'll start by multiplying the voltage and current together, and then I'll integrate the product and divide by the time to get power. In this case, I have 1 watt of power, and by the way, I get the same result if I just multiply the peak voltage and peak current and divide by 2. So in other words, this integration produces the total power in the entire spectrum, which is a combination of both RF and DC power. So what if I only want the RF power? Well, if I consider the peak-to-peak voltage and current signals instead of the peak signals, then I'm left with only the RF power. So in the time domain, using this approach can allow you to easily separate RF from DC. And don't worry if you didn't catch exactly how I calculated all of these things. Again, I'll provide a way to download this workspace at the end of the presentation, and you can see exactly how I calculated the power in these different ways. So the phasing between the voltage and current waveforms is really important for power, and this is a cosine function. So if I sweep the phase angle between the voltage and current waveforms from 0 to pi, or 180 degrees, it turns out that there's a maxima and a minima in the power, which just arises from the cosine. Now at the maximum point, the voltage and current waveforms are in phase, and this means that power is getting dissipated. And in practical transistors, power dissipation acts to convert energy into heat. Now on the other side of the graph, we have the case where the voltage and current waveforms are out of phase. In this case, we say that the device is generating power. And in the middle of the plot, power is neither dissipated nor generated, instead it's being stored. So here's an example of a circuit that we're going to use a lot in power amplifier design. This is an AC current source which is tied to a resistor. And since these components are connected in parallel, the current source and the resistor share the same voltage across them. But since the current source pulls current out of the resistor, the currents are opposite in the two components. So for the resistor, the voltage and current are always in phase because they're simply related through Ohm's law. But for the current source, since the current is going in the opposite direction as the resistor, the voltage and current are out of phase. So the current source is the power generator, and the resistor is the power dissipator. And you can determine this simply by looking at the sign of the voltage and current product. If it's negative, it's a power generator, and if it's positive, it's a power dissipator. Now, in any physically realizable AC circuit, there must be conservation of energy, so any power that's generated must either be stored or dissipated somewhere. And for this simple example, the power generated in the source is equal to the power dissipated in the resistor with nothing stored. So practically speaking, this type of circuit can be realized physically using a transistor connected to a resistor. And here I have a small signal transistor model like you might see in a textbook, and it takes the voltage at the input and then multiplies this by a gain factor and converts it to a current at the output. So like I showed before, the voltage across the load and the current source of the device are the same, at least for AC signals, while the currents are going in the opposite directions. But there's a little bit of a problem here. It takes energy to get gain, and so to provide this energy, we need a DC power source, which will create a bias on the device. And this DC bias will mean that the sinusoidal waveforms are actually centered around the DC operating point instead of zero. And we could do a simple nodal analysis at the output and show that the current that's supplied by the source is the summation of the current through the device and the current through the load. Or to put this another way, all of the power that's used in the circuit to provide gain and output power comes entirely from the DC source. So let me illustrate this. First, we have to note that the starting point at the current source is the DC offset, which is provided by the power supply. So let's see what happens when the input sinusoidal voltage goes negative. Well, that causes the current through the device to also go negative, and depending on the bias current, this can go all the way down to zero. Now, since less current is getting pulled into the current source, instead it flows in an AC sense from the power supply into the load. So this causes the current in the load to increase, and since the load is a resistor, that means that the voltage in the load increases too. When the voltage in the load increases, the voltage across the device's current source also increases. So if the input signal goes positive, then the current source draws more current from the supply, and this is more current than the supply is providing in a DC sense. So where does that extra current come from? Well, it gets pulled through the load from ground, and this decreases the voltage at the load, which decreases the voltage at the device. Now keep in mind that there's also a DC voltage bias on the device too, so the voltage here might be going from the DC value down to zero. So when I say they're coupled, I really mean they're coupled in an AC sense. And this is fundamentally how a power amplifier works. But there's one more thing that we need to consider. Since there's a DC offset across the device, power is not just being dissipated in the load, it's also being dissipated in the current source of the device. So let's take a closer look at this. Here I have voltage and current sinusoids, and these are offset by DC bias components. So here's the DC voltage, and here's the DC current. And these sinusoids are swinging from a peak of twice the DC value to a minimum of zero. We can also show the DC power directly on this plot, and obviously it's constant over time. And since these waveforms are always positive, to find the dissipated power, we simply multiply the waveforms together and integrate. The result will be positive, and this represents the portion of the DC power which is dissipated inside of the device at the current source. Now, if we remove the DC offsets from the RF waveforms, it's then easy to calculate the power generated, because we can just multiply the signals together and the result should be negative. Now, since energy is conserved, it also shouldn't be surprising that the area of the dissipated power combined with the area of the generated power is exactly equal to the DC power put in by the supply. So what I'm showing here are the waveforms for what's called a Class A power amplifier, and I just proved for this type of PA, at best half of the DC power will be converted to RF power. And as you might guess, this amplifier will be at most 50% efficient. So the concept of efficiency for a power amplifier should now be quite clear. At the output, the efficiency is defined as the generated power over the sum of the generated and dissipated power, or in other words, the generated power over the DC power, and this is often expressed as a percentage. So using the interactive waveform generator, which you can also download, it's possible to see what different types of waveform configurations will give you in terms of generated power, dissipated power, and efficiency. And it even tells you if a waveform is non-physical. In other words, it tells you if you have a waveform where the generated power exceeds the DC power, and this is a waveform that you can't actually build in the lab. And finally, let's talk about how to pick the load resistor. So to start, I'll take the configuration that I showed earlier with current source and a resistor, and I'll sweep the current in a DC sense. And then I'll plot the current versus the voltage, current on the y-axis, voltage on the x-axis, and I get a simple negatively sloped line. Now, the magnitude of the slope is equal to 1 over the resistance, since the slope is y over x, or current over voltage. So let's expand this simple analogy to a real device. For example, here I have a CMOS transistor, which is similar to the small signal model that I showed earlier. So if we take a look at the current versus voltage at the drain node of this transistor, we get a family of curves where each curve is the output response for a different input voltage. So to make this circuit operate correctly, we need to bias the transistor. So let's pick a DC bias point in the middle of the voltage and current range. Something like 250 milliamps and 5 volts will work for this case. So now if I go back to my current source and I add this fixed bias current into my current source and redo the DC sweep, you can see that the scales on the curve change, and now the line, instead of being centered around a negative point, is centered at 0. And 0 in this case is the bias point of the transistor. So we can just superimpose the two curves, and this is what is called a load line plot. It's very commonly used in PA design. So the load resistor is really setting the ratio between the peak-to-peak voltage and the peak-to-peak current. But it's important to keep in mind that this is also constrained by the device. For example, there's a knee voltage in practical devices which prevents the voltage waveform from swinging all the way to 0. So this needs to be considered in design as well. Okay, so if you want to learn more about the material that I discussed today, I'm making this workspace available for you to download. And it covers everything I talked about today, from calculating power directly from time domain waveforms to drawing a load line. And there's some more advanced capability here too. For example, you can set the bias current up to rectify, which will allow you to explore waveforms for more advanced classes of PA operation like Class AB and see how this improves efficiency. I think it's a great way to master these basic concepts. What I covered today really just scratches the surface, but it should give you a good starting point and technical foundation for RF power amplifier design. You can learn a lot more by downloading this workspace, including how I do all the calculations, and you can also see exactly how I set up the plots. And I put the workspace at the link shown below. Thanks for watching.